So we are going to extend Metropolis algorithm to 2 dimensions. Of course, we can do 3, but 2 is good enough. So the case that we are going to use is Bernoulli probability. Estimation for 2 parameters. Theta 1, theta 2. Or we can call it P1, P2. So we want to have, well, a good example would be rolling 2 dice, and we want to know the probability of getting a 2, right? In the first die, and getting a 2 in the second die, right? So that would be the probability of success for the first die, probability of success for the second die. But the issue here is we have to deal with joint distributions, do we agree? So when I say I want to get the probability of getting a 2 in die 1, getting a 2 in die 2, then when I do it together, or even in trials, there is a connection between the first and the second. So in order to reduce computational complexity, it's good to make an assumption. What is that assumption? Which works out in most cases. That they are independent. So let's assume that theta 1, theta 2 are independent. So the parameters don't affect each other. So that would mean we are going to have 2 different samples. One comes from theta 1, the other comes from theta 2. I like to fight burn. I feel it. Getting at the joke. X1, Bernoulli theta 1. I just laugh at my own jokes. Actually. X2 is Bernoulli theta 2. And we can have observations, let's say N1, the sample size. Here, there, N2. Standard notation, success would mean observation is 1, failure, observation is 2, which would not observation is 0, which would mean if I sum all, should probably put I, J there, because we are going to generate random variables of size n1. So I would be 1, 2, all the way up to n1. J, 1, 2, all the way up to n2. Good. Now, since independence is important, if we didn't have independence, the likelihood function theta 1, theta 2 given the data would be equal to probability I equals 1 to n1, excuse me, product j equals 1, 2, and 2. Then comes the probability data given theta 1, theta 2. Data in that case would end up being 1, 2, and 1. J equals 1, 2, and 2. x1i, x2j, given theta 1, theta 2. Yes? And they're going to work out in a joint manner. This is going to become pretty painful because first you've got to do the product and then multiply the product. But the multiplication part is not the issue here. The issue would be the function itself. Defining this properly in 2 dimensions or coming up with a density, that would be nice in this case. So we want to make them independent. If we did that, I can write x1i given theta 1 because x1i, those are simulated or sampled from a Bernoulli with parameter theta 1, multiplied by j equals 1, 2, and 2, x2j given theta 2. Mind you, when I write it, I don't write it as theta 1, theta 2, right? So this simply means, going back to STA 2023, when we write the probability of B given A, all we are saying is that B depends on A. It's just a notation for us, correct? So all we are trying to say here is this joint distribution depends on the parameters theta 1 and theta 2 together. But if I make them independent, x2j has nothing to do with theta 2, agree? Excuse me, theta 1, agree? x1i has nothing to do with theta 2. So I'm writing it as x1i, theta 1, x2j, theta 2. Good so far? Okay. That's just the likelihood function. Now, what would the posterior look like? We always know posterior, theta 1, theta 2, b. The notation is sort of funky there, right? Typically, the probability that you get parameter given the data, that is the correct way to write the likelihood. But because of the posterior, we should probably stick with that notation for the likelihood part. That's what we did even in maybe the first time we did the Bayesian matrix thing. So proportional to, I'll take this part, the inside part, so that we don't get confused. Multiplied by the prior. You know what? The book might do it this way. I'm going to do it my way. Posterior, likelihood, prior. Good. The prior is once again a joint distribution of theta 1 and theta 2. Sure, I can keep it as a joint distribution, but it would be better if I used properties of independence. So I can write this posterior theta 1, theta 2, given alpha, will be proportional to the likelihood of theta 1, theta 2, given delta, which in this case will be x 1i and x2j. Yes, I equals 1 to n1, j equals 1 to n2. I'm going to make the prior independent. So I can write this as prior of theta 1 multiplied by prior of theta 2. So that is the assumption of independent priors with me. And we already did this bit right here, the likelihood part. So erase it. So the posterior theta 1, theta 2, given the delta, which would be x1i, x2j. I can write this as P likelihood theta 1 given x1i multiplied by likelihood theta 2 given x2j. Yes, multiplied by prior of theta 1, prior of theta 2. Yes, now I can move things around. Likelihood theta 1 given the data simulated from theta 1 multiplied by prior of theta 1, likelihood of theta 2 multiplied by prior of theta 2. Yes? Good. So pretty much what I did is I wrote the joint posterior as product of independent posteriors. So the posterior here, theta 1 given x1i multiplied by posterior with theta 2 given x2j. I equals 1, 2, dot, 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 and 1, j equals 1, 2, dot, 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 and 2. So the thing that we learned here is if we have independent priors, we are going to end up having independent posteriors, provided the likelihood can also be written in an independent way. Good so far. So going back to our Bernoulli case, we know the likelihood here. We have to use this because that I did it to demonstrate that independence in priors result in independence in posterior. So independent priors.
The independent priors just a result of the independent parameters.
Yes.
And we can have likelihoods that are independent, but priors that could be dependent. Is it kind of like a binary where?
Well, you can't make this to be dependent. In other words, x1i, x2j, 2j are related in some way, and you can make those two independent, but you can't break them up like we did here.
Okay.
Right? We want independent random variables, which would mean independent thetas, prior, when we assume they have to be independent also. Only then you're guaranteed to have an independent posterior, right? The moment for instance, if I put this as a joint distribution of theta 1, theta 2, I can't decompose the way that I did, so it's not possible. All right. So it has to be this way to make things easy. Of course, there are complicated stuff in literature, in reality. Okay, so that's what we have, and we know a Bernoulli likelihood, do we remember? So what is the Bernoulli likelihood for theta 1? What does it look like?
Times 1 minus theta to the number of failures.
So that would be theta 1 to the power of, I'll call it x1, number of successes. 1 minus theta 1 raised n1 minus x1. x1 number of successes, in other words, sum of all the ones, and the likelihood of theta 2 theta 2 raised x2, 1 minus theta 2 raised n2 minus x2. x2 is the number of successes also, but corresponding to theta 1. Or let me write it as corresponding to x2j. The first one corresponding to x1 pi. So sum of all the x1 i's, I equals 1 to n, will give us x1, j, 1 to n1. J equals 1 to n2 of x2, sum of all the ones will give us n2. And that's the success, of course, n1 minus x1, n2 minus x2 will be the failures, number of failures. Okay, great. What about the prize? What did we use as a prize for a Bernoulli probability? A convenient prize.
Bernoulli probability.
For a Bernoulli probability, what did we use?
Wasn't there another Bernoulli?
The prior.
Oh, no.
I'll give you a hint, it starts with the letter B.
Right.
So to estimate a Bernoulli probability, we use a beta distribution. At the end of class last time, we were talking about choosing prize. So choosing prize, 95% of the time, primarily must come from your beliefs that you have from the past. The second layer of things is choosing priors that make the process easy for us. So in this case, choosing a beta distribution will make things easy for us because that looks like part of a beta distribution. Does that make sense? The first thing in terms of choosing priors should be your beliefs chosen properly based on previous research, literature, blah, blah, blah. And second thing, good densities or probability distributions that work out nicely. And that is the concept of having conjugate priors. Good. So the prior for theta 1, I can write it as a beta distribution, right? Theta 1, A1 minus 1, 1 minus theta 1, B1 minus 1. You see, you shouldn't be talking about A1s when you're hungry, right before dinner. So theta 1 is a beta distribution with parameters A1, B1. Good. Likewise, the prior of theta 2. Oh, I used lowercase r. Would be theta 2, A2 minus 1, 1 minus theta 2, B2 minus 1. So the prior distribution for theta 2 is A2, B2, beta, beta, A2, B2. We could have had R2, D2. No one got that either.
Oh, we got it.
She just ignored it. So, put them all together, we'll get the posterior of theta 1, theta 2. Look at that, magic fun. So, moving on. Oh, I can put proportional sign. Theta 1, x1, theta 1 raise x1. 1 minus theta 1 raise n1 minus x1. Yes, likelihood multiplied by its prior. Theta 1 raise a1 minus 1. 1 minus theta 1, b1 minus 1. Multiplied by theta 2, x2, 1 minus theta 2, n2 minus x2. Theta 2 raise a2 minus 1 multiplied by 1 minus theta 2 raise b2 minus 1. Mind you, we will throw in proportionality here because I don't have the normalizing constant, right? That's not going to integrate to 1. So, but that's why, I'm going to use the proportionality there as well. Good. Yes. Erase. Combine. Theta 1 raised x1 plus a1 minus 1. 1 minus theta 1 raised n1 minus x1 plus b1 minus 1. Yes. Theta 2 raised x2 plus a2 minus 1. 1 minus theta 2 raised n2 minus x2 plus b2 minus 1. What does that look like? Huh?
Another distribution.
So proportional, right? To what distribution? Beta.
Beta x1 plus a1 n1 minus x1 plus b1.
Yes. The other one proportional to beta again. n2 minus x2 plus b2. Good. So if we choose the priors to be betas, a1, b1, beta, a2, b2, under the assumption of independence, we end up getting that. The posterior proportional to product of independent betas, first one, x1 plus a1, n1 minus x1 plus b1. Second is that. If I want to get rid of the proportionality, which doesn't matter, right, when it comes to the simulation part, because we don't require things to be a proper probability density in Metropolis algorithm. But formally, if I have to write this and get rid of that get rid of that proportionality and put an equal to, I just have to derive this by a beta function x1, a1, n1 minus x1 plus b1, divide that part by beta function x2, a2, n2 minus x2 plus b2, then that distribution will integrate to 1. Good.